is Professor Tim Betting from the University of Sydney. Tim is a distinguished astroseismologist who's worked on many topics in pulsating stars. He was the head of physics, the School of Physics at University of Sydney for several years. And just last year, he was inducted into the Australian Academy of Science. And they made a snazzy video when he was inducted. So rather than listen to me talk, I thought I would just show you the video clip. So hopefully you all see it.
Professor Betting obtained his PhD from the University of Sydney before taking up a fellowship at the European Southern Observatory in Germany. He returned to Sydney in 1995 and is now considered a world leader in astroseismology.
It's really exciting to know more about our place in the universe, but there's still a lot we don't know, and that's why it's exciting to keep pushing on.
Okay, so I think you have an acting career ahead of you, Tim, as well as a scientific career. So please take it away with your talk.
Thank you very much, Jim. There are probably more embarrassing videos than that on the internet you could have shown, so thank you for not doing that. And thank you for having me. It's a really great pleasure, except of course I would rather be there in person, but I hope you're all doing well as can be expected, and that we'll be able to meet in person before too long. So Astroseismology, I'm going to talk about that, in particular, the amazing revolution that's happened over the last decade or so with the Kepler and TESS space missions. And of course, many, many people are involved in this work, colleagues in the two consortia. We have Astroseismic Consortia for Kepler and TESS. And so I'm not going to list everybody's names on here, but you'll see their names as we go through. So on the left, you have a picture of the sun from Gary Larson, but on the right, you have perhaps a slightly more accurate picture of a red giant. And that's what we're talking about. We're talking about the waves inside the star that propagate. There are sound waves in this red giant in the convective envelope. And in the center of this red giant, there are gravity waves, buoyancy waves. But we'll come to those in due course. But since this is a talk about stars, I will, of course, show an HR diagram. And this is one that shows all the various types of oscillating stars. And I'm not going to talk about most of them. I'm going to talk mostly about the ones in the bottom right, which are stars like the sun in that region, and also up the red giant branch. And towards the end, I'll talk a little bit about a different type of star called delta Scuti stars. But there's an awful lot of work being going on in the other parts of the HR diagram. In particular, white dwarfs are fascinating pulsating objects. And also up at the top of the main sequence, all of these hot blue stars, which TESS in particular is observing now. On the right is just one randomly chosen light curve from TESS, which is a space telescope I'll talk about in a minute. And what you can see if you zoom in on this is now covering about 2.5 days, pulsations, complicated pulsations, many modes beating together. And that's what we're all about. But it's always fun to go back in a bit of history. And given this is Caltech, it turns out that the 5-minute oscillations in the sun were first observed by Bob Layton. And he was, so this is in the early 1960s, he was using photographic plates on a solar telescope, looking at Doppler shifts of different parts of the sun. And he found, as in this picture here, there was about a 5-minute period in various parts of the sun. And it took quite a long time for people to understand what they were. And we now know they're oscillation modes that involve the entire sun. And so on the right is just one cutaway example of what such a mode might look like. This is a high degree mode with many patches on the surface. So a spherical degree of about 20. Now, of course, if we observe distant stars, we're not going to be able to see these modes. Instead, we're observing as a single point. And so I'll move on to talk about sun as a star helioseismology. And so we've moved forward to the 1980s now. And this is a beautiful power spectrum of Doppler shifts of the sun as a star, as a point, taken from the South Pole over about a week. And you can see in the Fourier transform a beautiful series of peaks. And every one of those peaks is an oscillation mode. And you can see there's a regular pattern with a typical spacing, which we call delta nu. And delta nu, we call that the large separation. And the figure in the middle there, that black figure, is I think just a photograph of a TV screen they made. It's another way of displaying the data, which turns out to be really useful. We call it an échelle diagram because it was made by French, and échelle is ladder in French. And so what you do is you divide the Fourier transform into exactly equal segments of width delta nu, and you stack them vertically one above the other in the ladder. And when you do that, the individual peaks line up in almost vertical ridges. And that's the pattern that you're seeing there. And we're going to be looking at lots of those today. But now we're talking about modes with much lower spherical degree. And this picture here is an example of a mode that only has L equals 2. And we can detect that on distant stars because the cancellation of different parts of the star doesn't reduce the visibility too much. So why does the sun oscillate? Well, it has a convection zone. And so another Caltech paper, Peter Goldreich and colleagues back in the 90s developed the mathematics and the theory of this. But if you prefer, I prefer the bottom version, which is basically to say convection excites the star, and it excites the oscillations by shaking it and creating many, many sound waves, which are standing oscillations, standing waves. And so it creates both the high degree and the low degree modes, all of them in great number. And so if this is the case, you'd expect any star that has an outer convection zone to do this, which basically means the right-hand part of the HR diagram. And so that drove people to look for these things. And I got involved in this work back when I was a postdoc. And here's just one early example. And there were several groups that did this sort of work. What we did was we used ground-based telescopes like the ones on the left, so the VLT and the AAT in Australia, with beautiful spectrographs with high precision velocities, which were in fact developed for planet hunters, because as I'm sure you know, planet hunting also uses high precision velocities. And so these are 3 stars. The middle one is the sun itself. We didn't take those data. But the one above and below are the 2 components of Alpha Centauri, the binary system. One is just a little bit more luminous than the sun, and one is a bit less. And you can see their oscillation patterns are strikingly similar. They all have this sort of characteristic hump of power, and we characterize the middle of that hump by something called nu max. So nu max is basically the middle of where the envelope of modes is excited. And we also have this regular spacing. And if we divide the spectrum up and stack it vertically, as I just described before, we can get an Echelle diagram for each of these stars. And you can see these vertical ridges, which I'm going to be talking more about. But notice they have different values of delta nu, and they also have different values of nu max. So that's obviously a lot of the information in there. So a lot of people were doing this. And around 2009, this is how things stood. Every one of these points in the HR diagram represents one of these stars. So Alpha Centauri A and B and a few others. By the way, the vertical axis is actually nu max. So it's the middle of the hump. And you can see as you go up in luminosity, the hump moves to lower and lower frequencies because the stars are getting bigger. So these are a few red giants up here, which are oscillating at much lower frequencies. If you're not used to these units, a microhertz, the sun oscillates at about 3,000 microhertz, which is about 5 minutes. And so you can sort of do the math from there. These stars are oscillating with periods of hours. So this is how things stood in 2009. Each one of these was hard work. And then the space revolution came. And the first up was Corot, which was a French European mission, about a 30 centimeter space telescope, mainly to look for transits, but also, of course, oscillations. And this beautiful paper appeared, which showed clear oscillations in lots of red giant stars. So the axis on here now is microhertz down in the 10s to 100. So these are low frequency oscillations, like little versions of the sun. Well, big versions of the sun. And so we went into this situation where we have now a whole bunch of red giants, and you can see the helium burning red clump here, and a handful of extra main sequence stars down here. And then came the day that changed our lives forever in March 2009, when Kepler was launched from a Delta rocket. And it's a 1 meter space telescope, no longer operating, but it operated for about 8 years. And the first 4 of those years were spent staring at one patch of sky in the north and around in Cygnus, over and over again, measuring brightnesses of stars. And so at a given moment, it could observe about 150,000 pre-selected stars with a sampling rate of about half an hour. And now that's half an hour is fine for red giants, but it's not fast enough for stars like the sun. But fortunately, about 500 stars at a time could be observed pre-selected with a much faster cadence, so a 1 minute cadence. And so we went almost overnight from this situation to this. And at this point, if I have a live audience, there's normally a gasp, because you can really see how a field could be revolutionized by such an enormous increase in data. Now, the color coding here is the amplitude of the oscillations. So down on the main sequence, they're pretty weak, only a few parts per million. And as you climb up through the red giants, they become stronger and stronger in their amplitude. And that's because the convection is stronger. There's just more energy in it. So that was sort of an early diagram. This is what it looked like after the 4-year mission. This is a diagram from GU's PhD thesis, and he analyzed about 16,000 red giants. You see a lot of them, and a smaller number of these main sequence stars, each one of which you can measure the delta nu or the nu max for. And then came TESS, and TESS is currently working. It was launched nearly, where are we now? April 2018, nearly 3 years ago. And it's covering the whole sky, unlike Kepler. But it's only doing so basically 1 month at a time. So each month it observes one of these strips, and then it flips around. And so if you happen to be near the ecliptic pole, you can get continuous coverage for a whole year. Otherwise, you're more likely to get coverage for only 1 or 2 months. The good thing about, well, one good thing about TESS, although it's a smaller telescope, it's covering the whole sky, and it's also orbiting the Earth and can downlink all the data. And so full images, the entire image with no pre-selection, is downloaded initially every half hour, and now in the extended mission every 10 minutes. So this is a full frame image of every star you can see every 10 minutes. And that's millions of stars. And in addition, pre-selected thousands of stars at a faster cadence, which is suitable for solar-like oscillations. And so this figure here, which was made for a grant proposal by Dan Huber, shows you the improvement. So the histogram at the bottom is the distribution of Kepler stars can be observed at rapid cadence, and there's several hundred of them. With the first TESS mission, which is the, and then the extended TESS mission, we then have this enormous increase in numbers of detections that we're going to be getting. Okay, so that's so much for the introduction. How do we actually do astroseismology and get science out of it? So this is a panel from an annual reviews article that shows 5 more or less typical Kepler stars. The top ones are solar-like main sequence stars, and then towards the bottom you've got red giants. So you can see the oscillations are moved down towards lower frequency, but they also look at the y-axis, go up in amplitude to much stronger amplitudes. And so as I've already mentioned, the center of this hump we call nu max is something you can measure. And it turns out that it's proportional to the surface gravity of the star and also depends on the effective temperature. So if you can measure nu max, you have measured something about the star, approximately. Much more accurately, you can also measure this spacing between the modes, delta nu, which I mentioned, the one that you use to stack the shell diagram. And that, it turns out, to a good approximation, scales with the square root of the density of the star, just mass on volume. And so with these two numbers alone, you've already done a lot. But of course, there's lots more you want to do. You're throwing away most of the information if this is all you do. So this tends to be what you use if you have many, many thousands of stars. But if you're looking at stars one at a time, you want to make full use of the frequencies. And so here's one example of a Kepler star. And now the diagram is labeled with all of the modes. So on the left is the ordinary Fourier transform, zoomed in so you can see the oscillation peaks. Each one of these peaks is a mode. On the right is the shell diagram, where you divide it into exactly equal segments and you stack them vertically. Actually, this is a different star to this one. It doesn't really matter. It's just for illustration. So the numbers along the top N are labeled, and also labeled up the side here. That's the order of the mode, the radial order. And the other number that's labeled in each mode is L, which is the spherical degree. So in these stars, we see either 0, 1, or 2. And you notice it has this regular pattern where it goes 1, 2, 0, 1, 2, 0. And by stacking them vertically, the ones line up in a ridge, and the twos and the zeros line up in ridges like this. So this is why the shell diagram is so nice to look at these stars. Oh, this is just a plug, by the way, for the package in Python called LightCurve with a K, which is available and fantastic. It's been written by lots of people, not me, students mostly and postdocs. And it's great for downloading and analyzing Kepler and TESS data. So what are these quantum numbers? Well, N is the radial order, and it's basically the number of nodes as you go inside a star. So you have nodes and antinodes. If you had an organ pipe like this, a one-dimensional thing, actually I happen to have one here, so this is just a flexible tube, and if I spin it around, I'll try again. So I hope you could hear that I could excite different overtones through this thing here. And so I was exciting the first, second, and third overtone. A star, of course, is spherical, but the principle is the same. You have within the star nodes and antinodes, which are spherical shells. And here's a cutaway example with a high N value. And in the stars like the sun, we tend to see quite high N values. So that's the first number you need. And then the second number you need is L. So as I said, L tends to be 0, 1, or 2. 0 means it's the star is breathing in and out completely radially. And then 1 and 2 are progressively more complicated spherical harmonics. So once you've done that and you've labeled this, you can compare each of these frequencies with a theoretical model. And that's the basis of astroseismology. But there's a lot of things you can do quite quickly. I already mentioned that delta nu itself, so this spacing that we're using, the average spacing between the modes, gives you the density. Another spacing is this small spacing between 0 and 2 you see in here. And that's generally called delta nu with a small delta. And that, it turns out, is very sensitive to the sound speed in the core, at least when the star is on the main sequence. And the sound speed in the core, of course, depends on how much hydrogen has turned into helium. Again, if I'm giving a public lecture at this point, I would breathe a helium balloon and make my voice go funny, because as you all know, the speed of sound changes in helium. I'm not going to do that, but you can believe me that these frequency separation changes as the star gets older. It gets smaller and smaller because hydrogen is gradually turning into helium. And that's basically how we measure ages. So with all of that introduction, I now want to talk about two aspects of astroseismology. So astroseismology, as I've already said, uses the frequencies of oscillations to probe interiors. The first thing you can do with that is measure properties of stars. So you have some stars you care about and you want to know the mass or the radius or the age of the star. And that's quite a big industry, especially for stars that happen to have planets around them, because it turns out the exoplanet hunters would really like to know how big their stars are. And then the second thing I'll do a bit later is more the physics. So what can we learn about the physics of stellar interiors from astroseismology? But let's start with a few examples of the first thing, measuring properties of stars. Now, as I mentioned, it's the planet hunters, and they keep us in business, and they're kind enough to put us on their papers. So here's one. Tom Barclay found a planet that was smaller than Mercury, so that made a big splash. In fact, this is a Kepler star which has 3 transiting planets, and one of them, or 2 of them, are quite big, but one of them is tiny. But before you can make a claim that it's actually smaller than Mercury, you need to know how big the star is, because all you measure from the light curve is the relative size of the planet and the star. You're seeing how much light is blocked. And so to measure the size of the star accurately enough, you want astroseismology. Now, you can't always do this, but some stars are bright enough that you can do astroseismology. We need lots of photons, and this star was. And so this is the Kepler's power spectrum of the star, and you can clearly see a regular series of peaks in here. And so with these data and models, we were able to constrain the mass and the radius to only a few percent and get a rough age. And this few percent on the radius was enough to put it in this category and get the title on the paper. So that's one example. Here's another one. In this case, it's another multi-planet Kepler system. This is Kepler 444, which has 5 planets. But the interesting thing, it's a very old star. And the oscillations in this case are beautiful. And the age we were able to measure is 11 plus or minus 1 gigayears. This is actually a typical uncertainty on ages. The uncertainty you get on an age, and I'm often asked this, is about 10% of the main sequence lifetime of the star. It's a bit like a fuse. So if the star is very young, the actual age, you're not going to get a very accurate age in percentage terms. But if the star is very old, 10% of its main sequence lifetime is 10% of its age. So anyway, this was another example. And then the third example is just the whole ensemble. So on the left here, you have the accuracy with which radii are known for all the main sequence stars in the Kepler catalog that Kepler observed. And so what you can see here is a function of effective temperature, so the sun's in here. For stars like the sun, most stars are known to a precision of about 40%, their radius, which is actually pretty awful, right? Because that's basically based on photometry. If you're lucky enough to have spectroscopy, then you get down to about 20%. But all the stars in the box at the bottom are bright enough for astroseismology. And in that case, you get down below 5%. So this is just a nice illustration. And a lot of people, including these people and others, have worked very hard on this, of getting accurate radii. And if you know your star, you know your planet. And this is just one nice example. Mia Lundqvist at the time was a student in Denmark. And she basically measured the radii of planets as a function of the flux they receive from their parent star. And so the Earth is over here. We get a flux of 1 and have a radius of 1. But if you move the Earth too close to the sun, it gets really, really hot. That's fine. But up in this region here, there's a gap. So these are the super Earths that don't exist this close to their parent stars. Now, the gray points are all of the known planets that Kepler found with quite large error bars. But the blue points have much smaller error bars because astroseismology has been able to give them a much more accurate radius and also a more accurate luminosity for the star. And so with the help of the blue points, you really become confident that there is a gap here. I'm not going to say any more about this because there are people at Caltech who know a lot more about this stuff than I do, so we should ask them. And then the last thing I wanted to talk about in this topic is red giants. So there are an awful lot of red giants, as I'm pointed out with Kepler, probably 15, 20,000 of them. And you can do a lot with them, even if all you do is measure their mass. Because if you can get their mass, you pretty much know their age. Because with a red giant, its mass tells you its age pretty accurately. And then you can do galactic archaeology, which is to say you can try to understand the Milky Way galaxy and its components. On the right here, we have the sight lines this is the galaxy view from the side and from above. And the Kepler stars are the green cone. And so Kepler reached out this sort of distance. And then the other ones that are colored are the Corot fields, where Corot observed. So this is sort of the sampling of the galaxy that you had. But then when you add the K2 mission, which came after Kepler, and now when you add TESS, you're really going to be filling out this volume and being able to really study the Milky Way galaxy. Now, this is an entire talk in itself, which I'm not even going to talk about, but many of the people are mentioned in these papers, and I'm sure there's lots of other papers that I missed as well. So galactic archaeology, using astroseismology with spectroscopy to try to constrain the Milky Way. Okay, so that's the end of part one. I want to spend the rest of my time talking about the physics we can do of stellar interiors, because we're all physicists, and after all, I think that's where we hope to make much of our progress. And again, I'm only going to scratch the surface, and again, I'll focus on things that our group has been involved with. There's lots of other things as well. So the first thing I'm going to talk about is something called mixed modes in red giants. So this is the picture I had on my opening slide. It's a red giant, and in the envelope of the red giant, which is convective, you have sound waves. These are the same waves I've been talking about. But in the core, which is basically made of helium, we expect it to be gravity waves. These are waves, a different type of oscillation mode where buoyancy is the restoring force. We can't see the core of the star, but it will be nice to get information about it. And that's, of course, the goal of astroseismology. And this is one of the most interesting things Kepler allowed us to do. So here's how it worked. Here is a red giant observed by Kepler after 1 month. And if you look at this Fourier transform, it looks quite like the sun. You can see it goes 0 to 1, 0 to 1, 0 to 1. The frequencies are a lot lower, but apart from that, it's kind of a solar-like spectrum. But you're starting to get a hint that the L equals 1 modes are doing something strange. You can see I put little bars on here. Now here's the same star after 4 years, and I'll zoom in so you can see a bit better. So the L equals 1, where there used to be 1 mode, is split into this enormous number, well, reasonably large number of individual peaks. Each one of these is a separate mixed mode. Meanwhile, you can see 0 and 2 are resolved because of the mode damping, but there's essentially only one L equals 0 mode in each case, but there are multiple L equals 1 modes, and these are what we call mixed modes. Where do they come from? They come because the sound waves, the P modes in the cavity, can couple to the G modes in the core. And the G modes in the core have a very dense spectrum. There are lots of them. And so what happens is that each of these couples to one of these, and you get a very complicated Fourier transform. Now, the theory of this was well understood even before Kepler, but I don't think anyone was actually expecting to see it. But when we did see it, we got very excited. And here's one of the most interesting things we saw. This is now 10 years old, this result, but it's so pretty I wanted to show you. These are 2 Kepler red giants, very, very similar, except if you look at their L equals 1 modes, you notice this one has a narrower spacing of L1 modes, whereas these ones are more spread out. And that's true as you look all the way along. And it turns out there's a very simple reason. The star on the bottom has started to burn helium. So this is a star that's reached the top of the red giant branch, ignited helium, and is now in the helium burning phase. In the HR diagram, these 2 stars lie almost on top of each other. But with astroseismology, we can see into the core, and we can see that this star here has a very different core to this one. And it's about a factor of 2 difference. This number delta P is the spacing between those modes measured in seconds. So there's about a factor of 2. So it's a very easy detection to make if you have good enough data. So that was a really cute example of astroseismology seeing into the cores of stars, and it's become quite an industry. The other thing I want to talk about in terms of stellar physics, and this is somewhat newer work, is rotation. So I haven't mentioned rotation so far, but those of you who remember quantum mechanics know that it's not just L, there's another quantum number, M, that describes spherical harmonics, right? Now, M is allowed to have values of, let's just talk about modes with L equals 1. You know that M is allowed to have values of -1, 0, and 1. Now, those modes are different modes, but in a normal star, they all have the same frequency. They're degenerate. But if the star rotates, they're not. I hope this animation's working. The star on the left is rotating one way, and the star on the right is rotating the other. And that corresponds to the prograde and retrograde modes. And if the star is rotating, those two modes will have different frequencies. And so this is completely analogous to Zeeman splitting. Remember, in Zeeman splitting, you turn on a magnetic field to break the symmetry, and you split one mode into 3. Exactly the same thing here, except this time it's rotation of the star that's breaking the symmetry. And this really happens. It happens in the sun, and people knew about it, but it also happens in other stars. So what happens is that the L equals 1 mode splits into a triplet. The central one, M equals 0, and either side -1 and +1. So you can measure two things from this. The width of this triplet, the spread of it, tells you the rotation rate. The faster the star is rotating, the more spread out these are. But remember, this is the rotation rate where the mode lives. So if you have a star which has modes that predominantly live in the core, like the gravity modes, this will measure the rotation of the core. If you have modes that live more of their time near the surface, this can measure the surface. In the sun, this has been done to quite a depth, and you can actually invert and get rotation throughout the sun. And I'll come back to that in a second. But the other thing you can measure from this, from the relative heights of the peaks, is the inclination of rotation. So what I mean is this: if the star is rotating like the sun, such that we're seeing it equator on, the Earth is near the equator of the sun, then we basically see the outer two modes, plus and -1. That's the dotted lines here. So the sun has an inclination of close to 90 degrees. But if we were to fly above the sun and look down on it from the pole, we would see the sun rotating along its axis. We would only see the mode in the middle, M equals 0. So if you can observe well enough and measure these relative ratios, you can distinguish between a star that's equator on and a star that's pole on. Why should you care? Well, I'll tell you who cares: the people who find planets. Because if you have a planet that's transiting, you know that the planets are in the plane that we're looking at, because you can see the transits. Yeah. And so wouldn't it be nice to tell whether the star is also rotating in the same plane? And this is a really nice example here that Dan Huber found, a star called Kepler 56. Now, this is actually a red giant star that has multiple planets going around it. It's a small red giant, but it's a red giant. Several transiting planets, and yet the star is not inclined, is inclined to its planets by about 45 degrees. And you can see that each one of these panels is a different L equals 1 triplet in the same star. And the ones on the top have the best signal to noise, but you can see, looking at all of them, if this star were like the sun, you shouldn't see the M equals 0. It should be very, very weak. You should only see the M plus or -1. The fact that you can see all three tells you that it's more or less at 45 degrees, and that's the value you get. So this is a system where the planets are aligned in this plane, but the star is misaligned. And that's interesting, because how could a multiple transit system have a stellar misinclination? And presumably it's an interaction with another star that's distant. This is obviously related to the Rossiter-McLaughlin effect, by the way, for those of you who know about that. It's a different way of measuring inclinations of stars. But I want to go back now to the other thing you can do. Remember, I'll just flick back a slide. The width of these things tells you how rapidly the star is rotating. And actually, you can see you get a different number depending on which panel you look at. So this panel here, it would appear to be that the star is rotating more slowly, and it's rotating more rapidly here. But the reason for that is that these modes on the top tend to be more G mode-like. In other words, they have more of their eigenfunction in the core, whereas the ones on the bottom are more P mode-like, and they have more in the surface. So between the two, you can measure differential rotation. You can measure the rotation throughout the star. And this was being done for quite a few red giants with Kepler. And the result was really quite surprising. And there are quite a few papers about this, but this is really one of the first ones. So basically, this is the rotation period of the core of the star as a function of radius of the star. So stars evolve from left to right in this diagram. But the problem is that the cores of these stars are rotating slower than expected. So let me pause and talk about this for a second. Right, the sun is rotating, as we know, and when it expands to become a red giant, conservation of angular momentum, of course, tells us that the envelope will slow down. Meanwhile, the core contracts, and so that should spin up. So you expect it to be quite a big difference between the core and the envelope in evolved stars. And there is, but the difference is not as big as you would naively expect from conservation of angular momentum. So that doesn't mean that angular momentum is not conserved. It means it's transported somehow within the star. I hesitate to talk much about this because Jim Fuller is one of the world experts on this, and he's probably talked to you about it. If not, you should ask him to. But there are mechanisms that you can use to transport angular momentum within a star as it evolves. And that's what the theoreticians are working on. And there's a dozen theoretical papers trying to explain these results at the moment. So it really is an interesting problem. At what point in their evolution does this angular transfer of angular momentum happen, and where does it come on and where does it stop? The problem is it's not easy to measure rotation inside stars. But I'd just like to show you briefly some new results, which Yaguang is a PhD student working with us. In fact, he's online right now. And these are some of his results based still on Kepler data. Even after all these years, we're still getting stuff out of Kepler data. So these are the same stars shown on two different versions of the diagram. So this is basically an HR diagram, and each of these is a subgiant or an early red giant, shall we say. And using astroseismology with Kepler data, Yaguang has been able to measure the rotation of both the core on the left and the envelope on the right. So these are both seismic measurements. Essentially, the core ones are using G modes and the envelope ones are using P modes. And the color coding shows you the periods. So what you notice is that the early subgiants on the left are rotating in the envelope about the same as in the core. But as you move and as stars evolve, the envelope is slowing down and the core is staying more or less constant. So you're seeing here a gap between the red giants I showed you earlier up here and the main sequence stars down here. This is still all very much work in progress, but I think it's an exciting area for astroseismology to be probing the rotation and angular momentum in stars. If I had time, I'd talk more about what you can do on the main sequence. There are a group of stars down here called Gamma Doradus pulsators, and we had a PhD student, Gang Li, who's finished now and is now working in Toulouse, who measured the rotation rates in the cores of a bunch of these stars down here. And a lot of other people have been trying to do similar things as well. But in the interest of time, I'm going to move on and talk about the last topic that I wanted to mention today. And this is probably the newest thing that we've done. And we actually got a paper last year, which I'll talk a bit about. And these are all the co-authors. And in fact, Andrew Howard is on here because we use some Keck data for some of these stars. And Jim Fuller is on here because he helped us understand what the hell is going on. And so what this is a result from TESS. So most of what I talked about today so far has been from Kepler, but now I'm going to talk about delta Scuti stars, which is a different type of star. But the theme of this work is that astroseismology needs mode identification in order to work, because what you want to do is compare your oscillation frequencies with theoretical models. But if you can't assign the N and L numbers to your modes, how can you do that? It's impossible, almost. So what are delta Scuti stars? Well, actually, they're very common. They're a type of pulsating star. They're basically A-type stars on the main sequence up here that happen to live inside the classical instability strip. This is the strip where the Cepheid variables and RLRs are also found. So the reason these stars pulsate is not because they're shaken by convection, which is what's happening down here, but rather that there's a heat engine operating with opacity acting as a valve. So the opacity changes in this outer part of the star alternately trap and release energy. That produces a heat engine, which drives the pulsation. So this is all well understood. The problem with delta Scuti stars is that they're very common, but the results from astroseismology have been very limited. On the right, by the way, just because I always love to show it, is the Gaia HR diagram. This is an unbelievable picture. It's just so beautiful. But the delta Scuti stars live up here, and there's an awful lot of them. So if we could do astroseismology with delta Scuti stars, even if only a small fraction of them, we could make some progress. So they're stars that have masses of a couple of solar masses or a bit less. So what's the problem? Why is mode identification so difficult in these stars? Well, there's a few reasons. One of them is that unlike in stars like the sun, not all the modes are excited. In stars like the sun, you see this envelope of power where pretty much every mode that should be there is there. They might have different amplitudes, but they're kind of all present. That's not true in delta Scutis. This heat engine mechanism is very capricious. And for reasons that are not understood, some modes are excited and some are not. That makes it hard to see the patterns. But even worse is the fact that these stars rotate quite rapidly. So rapidly that they're actually distorted from spheres. And the picture at the lower right is an image from the CHAR array up on Mount Wilson, near where you are now, of the brightest and closest delta Scuti star, Altair. And that's certainly not round. And so because the stars are aspherical, the oscillation modes don't follow these nice, as nice regular patterns of spherical harmonics as we've been talking about. There is a third thing too, something called avoided crossings of mixed modes, which I won't talk about, but it's to do with the things we were talking about earlier about mode coupling. So those things go together to spoil the pattern. Now look at the bottom panel. That's a pretty much typical delta Scuti star observed by Kepler. And I defy you to recognize a pattern in that. It's just almost impossible. By the way, the people who work on delta Scuti stars use different units for frequency. So the rest of my talk, the units will have changed from microhertz to cycles per day. If you care, there's a factor of about 12. So if you multiply these numbers by about 12, you'll go back to microhertz. But cycles per day is a convenient unit. These stars have periods of an hour or half an hour, something like that. So delta Scuti stars are good for something. They're really good clocks. It turns out their oscillations are very, very stable in time. And Simon Murphy and our group and others have done some beautiful work over the last few years using this to detect hidden companions, so binary stars, because over the 4 years of the Kepler mission, all of the oscillation modes in this star are moving backwards and forwards in time, in phase, due to the Doppler effect or due to light travel time delays. And so this has been a really nice piece of work. So at least delta Scuti stars are useful for something, but we really would like to do astroseismology with them. Now, this is where TESS came in. And I won't tell you the entire story, but basically trawling through TESS data, which is a lot of fun to do, I came across some of these stars. Now, these are Fourier transforms. Now, of course, they didn't come with the labels on them of L01. We added those later. But even without those labels, you can see they're pretty regular. In fact, they're amazingly regular. And we've never seen anything like this before. They're so regular that we could make a shell diagrams on the right by dividing the spectrum up into equal chunks and stacking them. We were greatly helped by Dan Hay, who was a PhD student here, who, this won't work now, but this is a slider that allows you to, in real time, move the spacing of your shell diagram so that you can get the right value. And pretty quickly, by comparing with theoretical models, we were able to decide that this ridge here was L equals 1, and this one here was L equals 0, and the same in this star. Interestingly, there's no sign of L equals 2, which in solar-like stars would live down here, but it doesn't seem to be excited in these stars. So this is very exciting because for the first time in a delta Scuti star, we have multiple modes where we can assign the L and N values, and we can compare them with models. And that's what we did in this paper. So this is just to show you that these are very different beasts from the ones I was talking about before. The upper panel is a typical Kepler solar-like oscillator, and it's much, much lower amplitude. Look at the y-axis. So these are very low amplitude oscillations. These ones are pretty high. These are up to a few millimag. Right? So these are detectable even from the ground. But also notice that N is much lower. So we're looking at modes with N below 10 rather than up here. Anyway, here's a gallery of some of the nicest 15 of them that we put in the paper. And you can see there's quite a few of them. And this was based only on the first part of TESS data. So obviously there's a lot more to find now. We are using the 2-minute data. Remember that TESS has pre-selected stars you can observe every 2 minutes. And that's what we're using for this. And so here's a bunch of shell diagrams for all of these stars. So by now you should be used to seeing these. The only difference I should point out is we've added an extension on the right for overlap because they wrap around. So you see you come across here and then you go up to the next line, and that peak there is the same as that peak just there. And so these open circles are theoretical models, which agree reasonably well with the data, especially given that the models don't include any rotation in them. And then the bottom ones are more examples of stars where we haven't made models, we've just drawn these red lines to guide your eyes so you can see the ridges. And so for each of these, we can measure delta nu, which is the value you need to make the shell diagram line up. It's the spacing. And here's a bunch more, just for fun. And just to show you that they're not all so pretty, here's a bunch that are much more complicated. So these ones here have multiple ridges at slightly different angles. And we think this is because these are more rapid rotators, or perhaps they're seen equator on. And so we're seeing multiple split L=1 modes in. By the way, this star here, Beta Pic, you might recognize. It's a known young disk star with planets. So anyway, the first thing we noticed really pretty early on is these stars are young. In the HR diagram, they're all hugging almost the zero-age main sequence. So the colored symbols are the nice delta Scutis that we found, and the dots are all of the delta Scutis from the old Kepler sample. And so you can see that they're almost all very close to zero age. And so that's why they have high frequency, right? These are high frequency stars. As stars evolve off the main sequence, they expand, their density goes down and their frequencies go down. Given that they were young, we did a cross-match with known young associations and moving groups and streams and so on. And some of the co-authors on our paper helped us with that. And of the 60 or so stars in our list, 7 of them were in known groups. Some of those names might be familiar to you. Beta Pic is a member of its own moving group. And the last one I'll draw your attention to, there was one star that was in a newly discovered stream called Pisces Eridani. That's an interesting thing. Now, the first discovery of that from Gaia data claimed that it was actually quite old because it had a red giant in it. But a follow-up paper by Jason Curtis looking at rotation said, no, that can't be right. It's only 120 million years old. Now, fortunately, one of our stars is in that association. Here it is. And the model that we have for that star indeed gives us a young age of about 100 million years. So this is something we're going to be doing quite a lot more of, is finding stars in these young associations and using astroseismology to measure their ages. Here's one we've done already. So this is a new paper that came out just last week. Simon Murphy is the lead author. Meredith Joyce at ANU is the theoretical modeler. She's a MESA specialist. And here's the light curve from TESS of this star. So this is a known star known to have a protoplanetary disk. It's in the Upper Centaurus Lupus group, which is part of Scuti. So this is a young nearby moving group. And the Fourier transform, when you look at it, you can see a whole bunch of peaks. It's not obvious by looking at it that it's regular, but if you make the shell diagram, it's certainly, you can see the pattern. So this is the shell diagram on the right. So the grayscale underneath is the observations. And when you've looked at enough of these, your eye can see exactly the same pattern that we were seeing earlier. So the L=0 modes always go down and curve to the right at the bottom. And the red points are the observed peaks, and the open circles are from the best fitting model. So again, we found a theoretical model that matches reasonably well the data. And the model, which is sitting in here, is pre-main sequence. So this is a pre-main sequence star. So it's coming down towards the pre-main sequence on its track here and hasn't yet reached the ZAMs. So this was a nice recent result for this star here. And what we're working on now are a few other things. We haven't even started writing this paper yet, but this is the Pleiades. Turns out there's some unpublished Pleiades data from Kepler K2, and a few of the Pleiades delta Scuti stars show beautiful high frequency oscillations with nice ridges. As I mentioned earlier, you have to work hard to clean up the light curves. Some of them are pretty messy, but this is work that's ongoing. Okay, so that's all I wanted to talk about. I have plenty of time for questions. I'll just say a couple of words about what's going to happen next. So Kepler is still going, and we're still using the data. When I was a kid, I used to watch those documentaries about the Voyager spacecraft going out through the solar system from JPL, just down the road from you. And I remember they said once, and it will take scientists years to analyze all the data from Saturn. I remember thinking, why does it take them so long? What are they even doing? Well, I'm sure I don't need to tell all of you how long it takes to get through all this stuff, but there is so much data still to use from Kepler, also from K2. And of course, TESS is delivering us data all the time. TESS has started re-observing the southern ecliptic plane, but at faster cadence. When it's finished the north, it will then flip down and do some of the ecliptic. And if all goes well, there's no reason why the mission can't continue for years. It's in a nice stable orbit and it's got plenty of fuel. And this is just to remind you, I showed you this already at the start. This is to show you from Kepler how many solar-like detections we could get. And this is what we expect to get from TESS in the extended mission, which is the mission that's happening right now. So lots of fun to be had, especially a lot of these stars are subgiant stars. I'll briefly mention SONG, which is a ground-based, I say network. So far, there are only 2 or 3 nodes, one in Tenerife, one in China, and one in Australia, just starting to work now. But the idea is to do radial velocity from a network. Plato is a European mission, a big mission that is currently being built. And the Chinese have really interesting, ambitious plans for a space mission as well, which they're calling Earth 2.0. So there's going to be so much fun to be had in the world of astroseismology over the next few years. And if you don't want to join us, at least consider becoming a user, because there's lots of things we might be able to do for you. Thank you.
Okay, thank you, Tim, for the brilliant talk. So we have plenty of time for questions. So if you have a question, please raise your virtual hand, or you can type it into the chat if you need to. Okay, Lynn, go ahead.
Hi, thanks for the very clear talk. I'm wondering if you could give us a more leisurely view of those very intriguing Pleiades results. They went by very quickly.
Yes, okay. Well, as I said, it's in preparation, but these are 4 known Delta Scuti stars in the Pleiades, and they were all captured by Kepler in its K2 campaign in fast cadence, so 1 minute sampling. And that's necessary for this. If you only have half an hour sampling, forget it, because the Nyquist frequency for half an hour sampling is down here, and so you just can't see anything. But you can say they all look quite similar, right? They all have a similar sort of structure. And when you make their shells, I hope you can see by now, these are not the best ones. This is sort of preliminary, but this is the ridge that comes down and bends to the right. And you can see it here, hopefully, and here. Not so obvious here. So what we're hoping to do is to bootstrap. In other words, use the good stars to figure out the other stars. But keeping in mind, this is a cluster, so they should all have the same age, same metallicity, and so on. And the L = 1 ridge you can see on the left here in some of the stars as well. So when we write the grants, we say we're going to use this to measure the age of clusters, but I'm pretty sure you know the age of the Pleiades. You don't need someone else to tell you. Maybe, well, correct me if I'm wrong. How well is the age of the Pleiades known?
Oh, well, I think it's pretty good now with the conjunction of, lithium and distance to the HR diagram. So I think we're doing okay on that.
Right. So in fact, for this group of stars, what you would hope to do would be to use the age as an additional constraint and to learn more about the stars. In particular, I mentioned all of the tricky ridges. I'll just quickly flick back because it's such a pretty picture and I went over it quickly. These are some of the TESS stars we saw. And these very thin extra ridges, which in these stars come from rotationally split modes. And I've talked to Jim a few times about this. So if you notice, the 4th Pleiades star, I hope you can see it, on the left-hand side has a very thin ridge just there. I have no idea what that is. But the point is that if we can use these stars as constraints, then maybe we can help the theoreticians, people like Jim, and there's Daniel Rees in France and others, Rita is only in France as well, who can make models of these stars and possibly figure out what the hell's going on with them. So I don't presume that we'll actually be able to tell you much about the Pleiades you didn't already know, although you never know, but I hope that you'll be able to help us understand these stars better. And when we do go to some of the other young associations whose ages are not so well constrained, then maybe we will have something to add.
Sure.
All right, next up is Shri.
I'm asking this question out of total ignorance. I've known for a while that A stars rotate rapidly. Why is it that they rotate more rapidly than B stars on one end and F stars at the other end?
Yeah, so not all of them rotate rapidly. There's a tail of the distribution that rotate fairly slowly, at least in V sin I, but many of them do, you're right. My understanding of this is that in cooler stars, they have magnetic fields because they have convection zones, and it's magnetic braking that slows them down. And if an A star doesn't have such a field, there's nothing to slow it down. Why B stars don't rotate rapidly, I don't have a good answer for that. I guess it must depend on the formation mechanism of B stars. I don't know if there's anyone else on the chat who can help.
I think most B stars do rotate rapidly. It's if you get to early Bs and Os, then they have enough mass loss that they lose a lot of angular momentum, and they rotate slowly again.
But that said, there's a group of slowly rotating B stars that have been around since the earliest days of people measuring B sin Is. And as Jim says, most of them are fast, but there's a bifurcation. There's a slow rotator group at kind of 50, 70 as opposed to 250, 300.
Yeah, and sorry, Shri, go ahead.
Yeah, another question I had was, I don't think the magnetic fields will have any effect on your astroseismology spectrum, but magnetic A stars have always seemed very fascinating to me. So has there been a study of the astroseismology of magnetic A stars, just out of sheer fascination of magnetic A stars?
So there's a group of magnetic A stars called the ROAP stars. Have you heard of them? Rapidly oscillating AP stars.
No, I've not heard of them.
They're very rare, but they're fascinating. They were discovered by Don Kurtz in South Africa. So these are basically AP stars, so peculiar A stars. They have slow rotation, strong magnetic fields, and many of them have dark features on the surface. And so they have rotational modulation, and you can see the rotation. The dark features, I understand, are caused by levitation of certain elements. Because the atmospheres are so still, because there's no convection and the magnetic fields kind of stiffen it, photons can levitate, and you get elements like europium on the surface of the star you wouldn't normally have. Now, some of those stars pulsate in quite high N, so more like the sun, N values of 20 or so, in very regular patterns. And there is a lot of, I can send you some literature on it, there's a lot of studies of those stars. And Don Kurtz in particular, who's now in the UK, but was in South Africa, is the world leader on that.
Okay, and the last question or comment I had was, there are many, Kepler has discovered many common proper motion stars, widely separated. So I would imagine they'd make good test bed for astroseismology, because sort of like the same idea as your moving group or cluster. You know that at least the one thing you know about them is that the same distance and same age. And so has there been a study of, this group of common CPM stars?
I'm not aware of one. I remember when I saw those papers coming out, I had a quick look and they all seem pretty faint. The problem with astroseismology is we need lots of photons. So it's really only the brightest. So it depends on the type of star, but if they're kind of main sequence stars like the sun, they have to be brighter than magnitude 12-ish with Kepler. If they're red giants, we can do a lot better.
But I bet we'll find a bunch of those with TESS. So I'm sure we'll see results on that soon.
Yeah,
okay,
that's a good
thanks.
point. Thanks, Sri. Nice to see you.
Okay, Sterl.
Yeah, so I had a related question, which is, of the many things that could be confusing all the rest of the A star or Delta Scuti star spectra, was you mentioned rotation. So is there a correlation between the V sin I measured from spectral line broadening and the simplicity of the astroseismic spectrum?
Very good question. I skipped it. I might have hidden it as a slide. Let me see if I've got it. We did, in our Nature paper, we showed spectra. And in fact, a lot of the co-authors were people from Keck and LCO and other places that, let me just see. Am I still sharing? No, I need to share again. There you go. So this is a plot from the paper. Oh, sorry, that's the wrong plot. I'm sorry. I'm going to have to dunk out again. Oh, maybe I didn't. Maybe I deleted it. Sorry. Okay, so I'll just answer your question. Yes, we think we see a correlation in the sense that the stars that have lower V sin I tend to have the nicer, more regular spectra, although not always. Now, of course, a star with a low V sin I could just be seen pole on. And a sample size at the moment is a bit small. But our kind of working hypothesis is that the really messy stars that are hard to interpret are indeed rotating rapidly and are probably seen more close to equator on. So remember when I first talked about the L=1 split modes, if you see a star equator on, you tend to see the outer modes or triplets, where if you see a pole on, you only see the middle one. And so some of the stars that are simple could be seen pole on. Beta Pic's an interesting one because Beta Pic has an edge on disk. Now, it may be that the star isn't aligned with the disk, but it is at least consistent that Beta Pic has a messy spectrum.
Okay, any more questions? So I have one, Tim. You showed some preliminary results for the subgiant core rotation periods. I was curious if there's any trends that you see there, because previously only about 6 of them had been done by Sebastian de Heuvel's, and there appeared to be a trend that the more evolved ones had faster core rotation. But I was always concerned that might be an illusion because they only had a few stars. So I was curious if your results shed any light on that.
Well, I mean, I really should be asking Yagwan to answer this, but here's his graph. And what you can see is that there's at least a trend. It's hard to see on this graph, actually. There are better trends, but there does seem to be a slight trend with mass. These are the higher mass stars up here and the lower mass stars down here.
But yeah, those are envelope.
I mean, we can either unmute Yagwan now, or we can talk a bit later offline if you like. Which would you prefer?
Yeah, we can talk offline. That's fine.
Yeah. I mean, Yagwan literally made this graph for me last night.
Oh, okay, great. That's very interesting. Okay, do we have any last questions? All right, well, maybe we can wrap up a couple minutes early today. So let's give Tim a virtual round of applause. Thank you, Tim.
Thanks, everybody. Stay safe and well.
And faculty, please stay on for the meet and greet.